Imagine a world where the idea of living to 150 is no longer science fiction, but a scientifically plausible chapter in human history. This notion is gaining traction thanks to breakthroughs in how scientists measure and interpret aging at the molecular level. Central to this shift is the development of epigenetic clocks, tools that can gauge our biological age far more accurately than counting birthdays. These innovations are bringing forward a future where extending healthy human lifespan becomes realistic. The concept of epigenetic clocks was pioneered by geneticist Steve Horvath, whose work began with the realization that the chemical markers on our DNA change in predictable ways as we age. These markers arise from a process called DNA methylation, where small chemical groups attach to DNA and influence how genes are used without altering the genetic code itself. By analyzing patterns of methyl groups at hundreds of specific sites across the genome, Horvath created the first widely used epigenetic clock that could estimate an individual's biological age with remarkable precision, often within just a few years of actual age. In a recent interview, Horvath explained that the ability to quantitatively measure biological age has changed the landscape of aging research. Rather than simply tracking the number of candles on a birthday cake, scientists can now monitor the subtle cellular changes that reflect real biological wear and tear. This allows researchers to test whether a drug or an intervention actually slows aging in people, rather than merely treating diseases that occur later in life. Epigenetic clocks have evolved since their humble beginnings based on saliva samples. Horvath and his collaborators developed more advanced versions that work across many tissues and even across multiple mammal species. One such model, known as Grim Age, estimates the near-term risk of mortality based on biological signals rather than simple chronological time. These innovations serve as critical tools for the longevity field, enabling objective evaluation of anti-aging therapies. So how does this relate to living to 150? According to Horvath, having robust and meaningful ways to quantify biological age is a cornerstone for developing interventions that could slow or potentially reverse aspects of biological aging. He believes that if scientific progress continues, and if humanity avoids existential catastrophes, then extending average healthy lifespan toward 150 years could eventually become a reality. However, he is cautious to dismiss ideas like living to 1,000 years as pure fantasy at this stage, emphasizing that such extremes remain far beyond what current science supports. Epigenetic clocks are already proving useful in research settings, showing that lifestyle factors, genetics, and environmental exposures influence the rate at which our biological age diverges from chronological age. These clocks can serve as early indicators of disease risk, offering opportunities to intervene before illness takes hold. Beyond their utility in labs, these tools hold promise for shaping a future where aging is not just an inevitable decline, but a measurable and potentially modifiable biological process. If humanity can develop safe and effective therapies that slow down or reverse the molecular hallmarks of aging, the social and economic implications would be enormous. People might remain healthier longer, reshaping retirement, work, and intergenerational life phases. In this emerging picture, the epigenetic clock becomes more than just a scientific instrument. It becomes a gateway into tomorrow. By decoding the molecular rhythms of aging, we inch closer to rethinking the very limits of human life.